All right. So again, just to make it clear, how this works is, again, we need to have a number of presenters. The presenters are just presenting. In other words, even if they don't know the material, it's okay. I want to make that very clear because this is a discussion group. Okay, so it's more helpful if we have a dialogue rather than presenting a lecture, okay, because everyone needs to be involved. Okay, so those of you who are in the support role, I think I saw Shin. I don't know whether you can use online, but you guys need to help take charge of the Slack, take charge of the meeting minutes, the document, along with the lecturing staff to populate it with useful information. So in particular, somebody from the support team needs to make sure that the document this week is finished by next week. Okay. So for example, last week in week 4, we had a discussion about BERT, which Kara and Abhinav took charge of. So hopefully those types of information are all in. Hello, I mean, so then that's how this will work. Okay. And we've decided to keep the multimodal models for week 6. And so I think I gave some feedback about where to start for that. And we'll have probably around week 10 or so a separate sharing session, which all of you outside of our group can tell everyone about what your interests are, your research are. Because I think, and part of the reason for making this discussion group and things like this public is to help my group network with more individuals who are like-minded. Okay. So without further ado, we'll start with Hoang's presentation. And please, even though this is a reading group, I hope you guys will interrupt, right, and talk, especially those of you who are outside on Zoom. Don't lurk, right? Do something useful and interrupt. Just raise your hand and tell us what this computer is about. So please just unmute your microphone and speak when you have something to say. I know there's about a 1-second delay, but we'll deal with that.
Okay, thank you, Prof. Min. I'll start the presentations. So today's presentation is on graph-based models. The presenter will be Christopher, KK, and I, supported by Hengchang and Guilherme. Okay. So graph-based model itself is quite a broad topic. So we'll try to narrow it down into geometric deep learning, which is how we apply the deep learning techniques into the domain of graph and manifolds. We're going to go quickly through its introductions, and then we'll also have some representations learning on graph. For some of my part, I'll be focusing on spectral graph theory. So over the years, we have seen a lot of success from deep learning. Deep learning has been quite successful in both NLPs, and even in computer visions. The successful test can be sentiment classifications, and also for images can be image classifications or object detections. So we're looking at the ways, so you know that there are more than just image or text, where so for image or text, we're calling it Euclidean data, because we can represent these kind of data into some kind of underlying grid structures in the Euclidean domain. But there are more than just Euclidean domains. There can be other types of data like graph or manifold, where such properties might not hold. So for graph, you may think that, can I just transform my adjacency matrix into some 2D matrix, and then I just put it into some kind of image classifications to do learning on graph. But you know that for your adjacency matrix, there's an underlying node orders. So when you permutate the two nodes, and you can obtain a different adjacency matrix, but the underlying graph structures remains. So when you do something like dot products in order to compute the similarity between two graphs, it may not give you one, but essentially the two graphs are similar. So such properties of Euclideans might not hold. That's why we're calling the data of manifolds of graph non-Euclidean data. So what tasks are we interested in learning in this non-Euclidean data? So we can do, so if our learning objects are graph, we can do some kind of graph-wise classification task, like molecules classifications. You can also do vertex-wise classifications. So given a citation networks consisting of nodes, which are the papers, and also the connections as citations, we can try to classify the topics of the research papers. And there's something in between graph-wise and vertex-wise, which is community-wise. And a classic task would be community detection. So anyone has any comments on this?
Community detection. Do you guys have any like interesting applications where you'd like to do community detection? I mean, there's some cases of here that Hoang has put up of say social networks, right? For both vertex-wise classification and community detection.
So in this case, the community detection part is similar to vertex-wise classification. Like we want some labels on each vertex, on the vertex.
Yeah, you could say that you have a label about which community you belong to, right? Vertex detection classification means like you're typing a vertex, but it may not be necessarily neighbor specific, right? So community is sort of thinking about distance between nodes rather than type of node. Any other inputs you guys want to say? Like if you're working on things that where there's contextual information that needs to be taken into account, graph convolution methods are useful, right?
So I just wonder if this community detection method, can it be applied to, say, for example, to detect outbreak of coronaviruses, maybe using news, for example, and then you want to add a Scribe, and then you try to do a community detection.
So Hoang would be a good person to ask because he's working on fake news stuff.
Yeah, technically we can. So yeah, we can try to, because if you read the news, there are like 5 clusters of corona right now. The ideas are that these elements belong to the same clusters, and say you're doing some kind of contextual sampling, right? You keep sampling the same set of neighbors. So like if there's some spreading patterns, and they'll be that cluster together.
I'm just curious, how would you model upon that? What kind of label would you use
For community detection?
Sorry?
For community detection?
Yeah.
So for community detections, usually we're interested in so there are 2 approaches, right? It can be some kind of embedding approach. I try to embed each node, and you do some kind of your favorite clustering algorithms, or K-means, where your inputs will be the embeddings code. The other way is that you just the other approach is something very similar to your topic modeling, where you have certain kind of underlying communities, right? That you're trying to put it together, and you're trying to maximize the likelihood of these nodes belong to the same community.
How would you represent a node?
Then there will be some concept of communities like conductance, right? So say definitions for community would be its outgoing edges is much smaller than its ingoing edges, like its internal degree is higher than its external degree. It's the probability of nodes being connected to the nodes of the same community is higher than probability of the nodes connected to the nodes from other communities. We're trying to maximize that probability. So it has underlying like probabilistic models. So that's for a more like direct community approach. You can look for methods like Louvain or InfoMap. I think for Louvain is more. And any other questions?
Can you capture because like there's now we heard about things like fake news as the outbreak of disease, and I guess there's a temporal element to that, right? Like there's a source there's a source vertex that like spreads outwards. Like, is it usually modeled as like one graph so that the H information will contain some kind of temporal information, or do you have like multiple graphs then?
Usually, we'll have so there are like 2 things. So in dynamic graphs, right? Usually your domain can be fixed. Say I have a fixed graph, and then the only thing that's changed is just the features of each node through time.
Okay.
So that can be one thing, right? And in that sense, then you think your graph is changed. You only need to model the features through time. But sometimes if it's an ever evolving graph, there may be new vertex and new edges, and probably you need. So one of the methods I read was probably to capture each graph snapshot, and model the pollutions of graph 2 times.
So we're doing fake news detection with graphs.
Yeah.
And you build a knowledge graph out of it.
Not knowledge graph. So I think for knowledge graph we have Liang Wing in here. You're familiar with knowledge graph.
Yeah.
If I'm not wrong, knowledge graph usually contains a lot of relationships.
Yes.
As it's very highly heterogeneous. So for my graph, it's also heterogeneous, but usually there'll be a handful entities like news or source or Twitter users, and also for the relations there are only certain relations, right? So it's not as rich as knowledge graph.
It's not as rich as a knowledge graph. So can I say that it's a subset of the knowledge graph? Or it's just like a weighted graph or something?
I'm not sure. Because usually
So just couldn't imagine like how would you do a fake news classification with graphs?
for which graph.
Yeah.
So the idea of fake news detection with graph that basically we want to capture the context of the fake news propagations. Right? So there was a lot of work that captured the content of the news, and then there's all the work that look into the social context, right? How it's spread.
And what would be the node and what would be the edge?
So the node will be like users, right? Which users engage with the news, and then the other nodes will be source that publish the news, and also the news itself, right? And how the different users connect to each other to form certain communities. So we have certain assumptions like there will be echo chambers, right, where users with similar interests will cluster together, and then for the nodes for the other nodes like the sources as well, like how do they to form five news communities, right, like left wings or right wings, Democrat, Republic. So I'll just continue. So so the key success to neural networks in this domain is essentially CNN. I know a bit offensive for RNN people. So so why such application to CNN is that successful? Because CNN there's these three properties of CNN. So the first one is actually shift invariance. So if you look at the inputs to the image inputs, right? So like this image of a bird, if it's right shifted or left shifted a bit, it's still a bird. So essentially, these signals are shift invariance. So in order to capture this shift invariance, CNN can the convolutional filters parameters can be shared across different locations. So that's why it can capture this shift invariance properties of the input graph, input image. The second one is locality. So the individual, so the way each pixel is represented is also influenced by its neighboring pixels. Say for this eye of the bird, like this black pixel, right? The way we are looking at the eye is not just because this pixel is black, it's also because that a surrounding pixel can be white, and then also its further pixels are red. So these kind of neighboring structures goes together in order to form some kind of semantic, abstract concept of an eye. So this is done because the CNN use relatively large filters that can capture the image features also from the local spatial neighborhood. And there's also the concept of compositionality. Like for this image, the compositionality essentially means that there's some kind of underlying hierarchy. So this concept is showing a bird, but there's a hierarchy. So this can be the bird, but there can also be the bird's head. And then from the head itself can also have other concepts like the beak or the eye. And this, the CNN can capture such compositionality or a hierarchy because it can stack convolutional layers on top of each other, and there's also pollings. And CNN is not only expressive, but it's also very efficient in terms of performance. So because of these filters are shared across locations, and so we have a fixed number of parameters per filter. So essentially it's all one operations. And for each layers, the convolution, because we're sliding it, so the computation complexity is essentially O(n). And because we are using a combinations of convolutions and pooling, so actually a number of layers is only O log n. So researchers have been looking into the successful of CNN and how we can generalize the convolution operations into non-Euclidean data. And when we look into non-Euclidean data, we can see the similarity in such kind of patterns. So graph itself is also shift invariance. So say given this citation networks, right? I want to represent this node, say node 26 is a paper. I want to classify this paper, the topic of this paper. And I look at the neighbors and it says that node 25, 32, and 24 are about NLP. So I want to aggregate such information in order to classify for node 26. And then across the graph, I can also see similar patterns, like the surrounding nodes of node 7 is also about NLP. So I can apply the same logic across all different locations of the graph. So this shift invariance is essentially a consistent applications of neighboring features, regardless of the node location in the graph. And there's also a concept of locality as well. So our CNN-like operations on graph should be able to have some kind of proximity sampling so that it can capture the features in the local spatial neighborhood. And in graph domains, there's also the concept of compositionality. So there's also a hierarchy, like this whole large graph, and then there can be smaller subgraph, and then can be a community. And within each communities, there can be individual nodes. So our roadmap for generalizing CNN into non-Euclidean, so we want to extend CNN-like operations into non-Euclidean geometries by replacing the filtering and pooling operations with appropriate operators.
Can you go back like a couple of slides?
This one?
No, the CNN shift invariant.
This
Yeah. What does it mean sharing convolutional filters across all locations?
So
It's just sharing.
yeah, sharing. So the idea is that
And how
this convolution filters, they're not being specific to any locations in the image, right? So it's not like learning different parameters for this part or for this part or a certain part. So another approach to learning image can be you just squash it into flat vectors, right? And you just learn like huge parameters. But in that sense, that you lose out the shift invariance, right? Because for each location you have a different parameter, right? And it's not shift invariance, but if you have convolutional filters and you slide it, then for each location you have the same convolutional mechanisms, right? And you can capture, say, the features regardless of its location.
Are we all clear about how a convolutional filter works? Right, so you have a single filter, and usually n by n filter, right, being applied at every spatially located patch in parallel, right? Even though we think of sliding this convolutional filter across an image, actually we're doing it in parallel because we have GPUs, right? So every patch is being assigned to a GPU, and they're all using the same parameter weights, right? It's one filter that is entirely being updated by all of the different patches being gone through at once. So, right, so let's say you have a convolutional filter that's looking for a vertical line, right? It's looking for that vertical line filter at all of the different patches where each GPU is looking at a specific segment or patch of the image. Right. So I think that's what Hoang means by shift invariance, right? So you're looking for the same feature at every part of the image. And when you pull, if you're still tying weights across layers, which we don't usually, but it means that we can find the same type of features at different resolution levels, right? So you have a small face in the background, a big face in the foreground. Ultimately, when you do pooling, you could use the same detector for both, right? Because the big face will become a small face after pooling, after several levels, right? It'll be reduced down 50%, 50%, 50% until it's the same size. And the same 3x3 or 5x5 filter will pick it up. Everyone clear about that?
Just how do you input the graph to the CNN model? I think you were mentioning matrix form when you were starting your presentation, but is that the standard way to?
We'll show later.
Oh,
So
sure.
there's actually two approach to inputting graph, right? There's a spectral approach and there's a spatial approach. So spectral approach, similar with you're breaking down your agency matrix into something like eigenvalue decompositions, right, into its spectral domain. And there's also a spatial approach, which means that you're just going through like each node and you're trying to pull the information from its neighbors. Something like that. So for my part, I'll be talking about the spectral based approach, which unfortunately the part that requires a lot of math.
So next slide did an analysis. So next slide did
Yeah.
analysis on the
This one, right?
the bottom right. So you just said that there's a whole log n layers in classification tasks. So
Yeah.
it's a big O log n in terms of number of operations
It's,
or
is it a number of layers?
number of layers. So like, does that mean that what would be my n in this case?
And in this case is the size of the image.
Size of it.
Yeah, because we use like it's in standard like in most popular CNN architecture, we use alternate combinations of convolutions and polling, right? So the polling itself is actually we're using that.
I see. So that's how that is.
Yeah. That's how it is.
You repeat that? I don't think everyone caught it. I didn't catch it. So.
Okay, so n in here is the size of the image. It's big. So it's all of n in terms of layers because instead of the CNN based models, we're using a combinations of convolutions and polling. So that's all.
Only if you use particular filter sizes for max pooling.
Yeah, but I mean, it works. You're all clear about how these properties can also be translated into Euclidean data. This is probably a shift invariance, locality, and compositionality.
That's what I wanted to ask. Like, how does this map to
Oh yeah.
shift invariance, especially the other ones are okay, but
So shift invariance, you can see, say I have a citation networks graph, right? And then I want to do some kind of node classifications on this. And say my node classification task is to classify the topics of a paper. So then I have the topics of, I have some features of its neighbors, right? Say this one is about NLP, this one about NLP. So my convolution or whatever operation will try to pull these operations from its features and try to come up with say topics of this one, probably NLP, right? And then across the graph, say in other locations, right, number 7, I also have the same features, same neighboring features, talking about NLP, right? Then I should be able to apply the same logic, apply to the node number 26 into node 7, right? So it's shift invariance, right? I can apply the same logic across the graph. It's like some kind of a convolution filter, so I can slide across all the graph, have the same application logics from the neighboring features.
so are you saying, okay, even if the nodes are geographically, in the graph they are located at different locations, that's the shift.
I think we put in the between images and graphs is that like when you have an image you have the sense of space. So like if you going right, a pixel is next to another one, so you can go right, up and down. But with graphs, like there's no such a sense of direction. So that's why it's sometimes can be a bit tricky to talk about shift invariance because like if you have a filter that passes through an image, like like the filter is multiplying what's on the left side and what's on the right side, but then with the graphs you have to define a way that you have to define some way to say, oh, this section of the graph looks similar to another section of the graph. So like one way to say that like it's connected just through like similar neighbors and stuff like that.
Okay. And also the concept of locality, like how the modelings of single nodes can be affected by its neighboring nodes. And the concept of compositionality is like there's a hierarchy of structures, like subgraph and then community and then individual nodes. so the roadmap, we're trying to extend the CNN-like operations into non-Euclidean data. So, so next I'll be talking about spectral-based methods. So a bit of graph theory here. So you know that say this is our graph and this is G. So we're all only looking at undirected graph for now. It can be weighted or not weighted, and it will be 1, 0 for each edge values. And then this vertex space will be V, and then the edge space will be E, and there will be edge weight. Okay. So what's the target functions that we're interested in? So we're interested in learning this class of functions. We're trying to map our features from the vertex space, into some real value space. So this is represented as this set of functions F.
So in the image analogy, that would be the fixed intensity.
Yeah.
So here the vertex.
So
Like if it was an image, it would be the pixel intensity. Here you're talking about the values, what the values of each node map to a number.
Oh,
Yeah.
so it's more generalized.
Yeah. Yeah.
and then the outputs of applying this function F into individual vertices will be F1 into Fn. So in representations learning, we're also interested in the smoothness of the target functions that we're trying to learn. So one way of measuring the smoothness is we're trying to measure the outputs of the functions on values, and also we're trying to measure the difference of the output of function on the values and its neighboring values. So you can think of it as how drastic the functions change over some smooth curve lying interface.
I can also say that, like, to the idea of the, so in the image case, you have the concept of the gradient. So if you go from one pixel to another, like you're increasing the pixel intensity from 5 to 10. So in the case of graph, like the edge will be the gradient. Like, so because you're not in the Euclidean space, like that, you can have the directionality, doesn't matter, but still you have the concept of vectors.
So the matrix that represent how they represent the difference between the output of F of a node and its local average is called a normalized Laplacian graph. So say in this graph, then Fi will be equals to F itself. The difference between F and also its local average. Right?
It's like a weighted difference, I guess, between itself and the matrix.
Yeah. You can see it's mathematical formula. And this is a positive semi-definite matrix. So we leverage this into the Dirichlet energy, which is the direct measure of the smoothness. Basically, this square, and it's also a reflection of how fast this changes locally. So our learning problems is basically we're trying to find, so in every functions or transformations, there's a set of bases that form such transformations, and we're trying to find the set of bases such that it gives us the smoothest functions. So we're trying to break down the spaces into measuring the smoothness of this individual basis with some constraint that these must be orthogonal to each other. And so this is our optimizations problem. We're trying to minimize the trace of this trace of this product with subjects to the orthogonal constraint. So the solutions to this is actually the eigenvectors. The solutions to these bases is actually the eigenvectors of the Laplacian matrix, which is this matrix.
Can you say that in, let's say, layman's English? What are we doing here?
Yeah.
Because I mean, the math is fine. I think this is all good. but when we're decomposing it into a set of orthogonal bases, why do we want to do that, and what's the end result?
Yeah. So the idea is that we're trying to learn these functions, right? And these functions, because it's mapped from B into R, and there'll be at least n times our directions, right? Say, so I want to map from each node into output, say k, there will be n times k. So there'll be a very large matrix. So what we're trying to do is that we're trying to see if we can narrow down the class of functions we want to learn by having some constraint that it has to be the smoothest class in it. So that's why we're trying to solve for this problems, and we realize that there's a basis of these functions. These functions actually have belongs to some subclass that forms by this third basis, and this third basis actually it's actually the eigenvectors of the Laplacian.
So the Laplacian is kind of like it's the convolution operation is or a proxy for finding differentiation over the images. We are doing something similar over the graphs here. So that is delta, right? That is the Laplacian. The delta here is Laplacian, right?
This doesn't have to do, I mean, we're not in the convolution yet. It's just like,
Right, but the Laplacian is kind of finding how the functions change in the vertex.
yeah.
Like how does the function change from one vertex to the other? How
The locations are actually more of characterizations of the graph.
Yeah, like maybe like we can like you try to find like functions that go from one to n, and then like let's say any function you can define in the graph, like the pixel intensity in the case of the image, but any function you can define these vertices has a value of 10, this vertex has a value of 5, and then like your features are defined by a function. Like so this vertex has a value because of a given function, and then you're doing something similar to what you do in a Fourier transformation. You're trying to decompose like this function into a lot of different functions that the sum together would give you like the underlying function.
Yeah.
So but what's the other what type of functions are you looking for? You're looking for a function that varies in the following order, like a function that's such that the Laplacian is the minimum. So my first function will be a function that if I go from vertex A to vertex B, I would like that this function, the vertices values don't change. So let's say this function, the value is 1, and then the next vertex, the value will be 1. So in that case, I'm saying that my energy, I'm looking for a function for which changing vertices will minimize my energy. So like changing from one vertex to another, my energy will be as minimal as I can. And at the same time, this verticing has to subject to a certain constraint, which is like that it should be equal to 1. Otherwise, it could have as many functions as you want. And then you're gonna find these other functions that will vary from like.
sorry, I think so I'm not sure, but this is just my own interpretation. But I think there's another motivation other than the fact that this is actually smooth because like ultimately we want to define convolution, right? And it's nice if our convolution can be shift invariance, possessing all those properties. And I think the fact is that in signal processing, like people has their own convolution definition, which can actually we can implement this easier in the space spanned by the Fourier basis. And it just happens that the Fourier basis is actually like if you decompose the Laplacian matrix, like those orthonormal bases actually forms the Fourier basis. Yeah, so that in finding the Laplacian, you can find the Fourier basis that easily spans your space, and you can run convolution easier in that space.
Yeah. But this is only true in the case of the Euclidean space. That you find the Laplacian is equal to the Fourier in the Euclidean space, and then in the other spaces it will be something that's equivalent to the Fourier transformation. But
Yeah. So I think the idea is that there's a nice parallelism between the eigen decompositions and also Fourier transformations, right? In a sense that these eigens vectors also form the basis of the Fourier transform. So you can see that in here we're trying to plot the graph of the top eigenvectors with the highest eigenvalues, and it indeed from a very nice Fourier transform. And also this parallelism also help us guarantees in the Fourier transform space, right? Because in Fourier transform you can apply the concept of convolution as well.
So can we say that it has a computational efficiency, or what do we want other people to take away from?
I think the key takeaway in here is that these decompositions have a theoretical guarantee that it's model the true concept of convolutions in signal processing. And I think that there's also efficiency takeaway in here is that instead of trying to learn a functions, say essentially it's end-to-end. Right? When you break it down into say eigen decomposition, you only need to learn this diagonal matrix is essentially just n.
Can you go one slide?
Yeah.
So, what is the objective function? Like EDIR?
Oh, DIR is one is Dirichlet energy.
Oh,
Yeah. So here is measured.
okay. And minimizing that makes the transition between the vertices smooth,
Yes,
right?
smoother, yes. So because the graph notations it can be calculated beforehand and it's not dependent on the functions we're trying to learn. So the graph notation itself is just this d minus w, where d is essentially the diagonal matrix of the diagonal matrix of this degree matrix, and then w is just the weights. So we have successfully break down our graph notations using eigen decompositions into these two set of eigen vectors, and together with the diagonal matrix of forms by eigenvalues. But still, there's a problem because these filters are still basis independent. So you can see that this W is n times n diagonal matrix, and there's no guarantee that these different bases will have some kind of generalizations, because we also want a stronger strip invariance. And for each, so there's the ON parameters per layer, because this n times n, it's n parameters in here that needs to be optimized. And also calculating this forward Spiro transform on graph is actually O n squared. Not to mention that in order to do an eigen decompositions is actually O n cube, O n cube. And there's also no guarantee in the spatial localizations of filter.
Like the O squared computation for forward. How do you get the O squared? Probably it's like n log n or something.
I think it's n log n on the
Fast forward tracing,
yeah. That's Euclidean, right? In this case, graph.
So how did the graph polynomial? How do you
It's okay if we don't know.
I'm just curious.
Yeah, that's a good question.
Not sure about why we cannot define. I'm not sure about the details on why we cannot define phosphor transform, because that was makes like n of n, right? But probably because this is transfer just some matrix multiplication.
Probably
Probably because like they're defining the Euclidean space, so like it probably depends on the variations defined by the distance. Whereas in graphs, you probably cannot define distances because the vector depends on the edges, and then you cannot say that you cannot define like what it means to go from x plus delta x. Whereas in Euclidean space, you can do that, and maybe because of that, you can define a fast Fourier transformation. But I don't know. I'm just speculating because I don't know anything about FFT. But just using the property, but thinking about the properties of one space and the other space.
I'll send you the. Okay, if you want to know more about all these theories, like how is this derived, there's actually a link below. It actually comes from geometry. Yeah. I think it comes from the survey geometric deep learnings beyond Euclidean data. It's come from these tutorials in NIPS. You can check out the tutorials and see more details on these derivation.
So something I didn't understand quite is the weight. Like when I was reading the paper, like so basically here you're substituting the matrix W for what originally was the Laplacian.
Yeah.
So what's the idea behind that?
What's the idea of?
I like now the W is in the place of the delta in the Laplacian. So like what are you doing then? Like because if you had the Laplacian there, then that function f would be equal to this times f. No?
Yeah.
But now now you're trying to apply a function of weights W to get G, which is a different.
The idea is there you want to convolve like f with w,
Mm.
and in order to do that, it is actually equivalent to multiplying like the value of the filter with the Fourier transform of the function. So if you see there's was that phi psi that you see that I think it's phi transpose f, that is actually the Fourier transform of f. Then on the Fourier space you can multiply with w, and after that you multiply again by phi to inverse Fourier transform that to the original space.
Oh, okay. I see.
And that is equal to convolution.
So it's like you try to project this f into the eigenspace, right? Using this phi transpose.
So then okay, so you go to the eigenspace, and then now you want to apply different weights to different eigenvectors. So this eigenvector actually is worth more than the eigenvector.
And I'll say that because now we have this diagonal matrix, right? So the dumb parameters we're trying to learn for this transformations in the eigenspace is actually just n. Like instead of just directly optimizing for this huge matrix, right, which is n times n.
Okay.
And this basis was actually derived from the smoothness, optimizing for smoothness we just done earlier.
So the matrix R is diagonal, so you're always finding n weights, only n parameters.
But still, this is still not very effective, right? Because when in true convolutions, what you want is O1, not On for each filter.
Oh.
This one is still On.
Okay. But if you say like I only wanted the first 10 features, then is it possible? Sorry, if you only want to use the 10 first eigenvectors instead of the full.
Is it first eigen?
So I think what you're asking is, can we reduce the rank? Right?
Yeah.
Can we approximate by throwing away unnecessary dimensions in the basis? Right, just like we do for SVD, right, or any other type of compression mechanism. You find the top n orthonormal bases, right, and then you throw away the rest. And you say, well, those are low end approximations. They're higher order functions. I just want the basic.
I'm not sure anyone is wrong to that, but I think by breaking the basis, probably it will kind of infringe the
Because I think in the paper they actually say that they only use the K first, right? They rank the first.
Or do they use the this one? Or is it because after they obtain Shibuya?
Yeah, even before the
I think
they say they can still
do it.
K because because the whole is like SVD, or even if you do the image convolution, it's like imagine if for each image you're gonna get a convolution the size of the image, so the equivalent in graph would be to get only the K first, a rank of K. But then the problem is that since every graph is different, then you can't do the same that you do for images in the graph, because then the transformation is different for graphs. Whereas for images, it's always the same, but it's a square.
So I imagine that using if you use something like PCA, right, and you're trying to guarantee some kind of variance, and probably it's still the numbers might scale with the size of the matrix, right? It's still O n somehow. You cannot do it. Say I want to preserve 90% of the variance. You're doing DCA or any kind of SVD. So
you're saying you cannot analyze 9% of variance?
Yeah, I mean, I cannot, because you mentioned, right, the graph very different. So
Yeah.
say I want to preserve, say, about small graph, you can use like first 10, right? But what happened if my graph is very large, then using the first 10 might not be enough.
Oh, yeah.
Yeah.
Yeah. But like it's the same with the image. Imagine like if you have an image here says 8 by 8 pixels, then use a convolution like that is of a given size. Now imagine you have a very high resolution image. Then like convolution, then a layer that it has only like 2 by 2, like it's not gonna do anything. But I guess like sometimes I think you can like when you use a PCA, like maybe you're interested in analyzing 9% of the variance because maybe the 10% is just noise, so there's no point in analyzing that.
Any other questions or things? Okay, so can we summarize what we're getting out of this? We're doing the transformation to get a set of basis functions that represent the overall transform. And then what we want to do is learn the weights on these basis vectors rather than on the entire function itself, right? Because we believe that we get the weights for the component basis when we multiply through, we recover an approximation of the original function, right? And like what we were just saying, perhaps it's okay to reduce the rank of the basis vectors instead of using the entire set, because then we can remove higher order interactivities, which still may approximate the basic function. Okay. Yeah.
I'll continue. Yeah. So solutions, what solutions in the papers by Kip and others is, the solutions presented in this paper is that they're trying to apply some smooth spectral transfer functions into all of the parameters. So like instead of learning a separate parameters for all this, we're going to learn transfer functions can be applied across all the eigenvalues. Yeah.
Sorry, slide 17. Yeah, so just going back. So lambda 1 to lambda L are non-negative eigenvalues. Shouldn't they be non-negative? They should be non-negative, right? Always.
I think they're non-negative because this one is semi-definite. Positive is semi-definite.
Yeah. So it should be non-negative, right? Yeah. The eigenvectors of positive semi-definite is always positive.
Sorry?
Are always positive.
Eigenvalues.
Eigenvalues.
Not negative, so it can be 0.
They can be 0. Yeah.
0 or positive?
It's
0
it's semi-definite. It's semi-definite. Yeah. So it can be 0.
Yeah, just like a correlation matrix, right? Even that's a positive semi-definite, but it's always positive, the eigenvalues. But why do they mention that it's not negative? Because it can be 0.
Because the Laplacian, like you subtracting the W minus D, then because it's subtracting the diagonal, it cannot be.
It's symmetric, so
it's symmetric because it's not inverted.
So this spectral transfer function can be represented as a function of polynomial on of R. So the takeaway here is that we don't need to learn separate parameters for each eigenvalue. You can learn underlying spectral transfer functions that is parameterized by R parameters, in terms of polynomial. And this helps because now basically it's all R, because we can keep R arbitrarily low, so it can be as all 1 parameters per layer. And it's also this R-half support where you can vary R for better approximation. And so for this point, there's no explicit computations. Is because you can factorize this into a very nice products of this matrix. You can see this A can be your normalized allocations, this X can be your input features matrix for each node, and then this W can be the weights you want to learn for each layer. So this analysis put the foundations for the very first papers on graph on the efficient graph convolution networks by Kip and Williams. So in order to know like how does this spectral transfer functions becomes this very nicely formulated matrix product, you can check out the papers by Kip and Willing in 2017. So that's all from my part. Any other questions? Oh, yeah,
I don't have Zoom either. So we have one. Okay. That's it. Let's speak through.
How long is your presentation? I don't know. I can actually like 5-10 minutes.
Oh, okay.
There's a couple of slides, like 6, 8.
When you read the papers, did you learn anything about like how does this method compare in terms of performance after you've done this transformation, like with the image, convolutional image?
Oh, you mean the performance between convolutional on graph and convolutional on
Yeah, like applying this paper.
Oh yeah, you can check the paper.
Ah, okay.
I think it can.
Oh no, but I just want to remember, but I can check out.
Yeah. So basically, it addressed the problems. Okay, first of all, it addressed the problems of ON parameters per layers, right? Because there you only have O1, which is very similar to your convolutional filter. Second one is that you don't need to explicitly decompose the eigen, to do the eigen decompositions of the Laplacian matrix anymore, right? Which will save you from the O and Q. And because because you're approximating it using some smooth spectral transfer functions, and there's some explanations that this one can help guarantee the localizations in space. So you can also guarantee the spatial localizations of the filters.
But you still have to compute the eigenvector.
You don't need to compute the eigenvector. So you can see the final formulas becomes this. So this is a very it's our favorite feed-forward neural networks, right? So you need to break down this normalized Laplacians anymore.
Okay. So do you know what's the equation that he uses to go from the phi to the phi? So how does this part I understand, but how does how does he skip the phi calculation?
He didn't keep five.
I'll talk a bit about that, I guess, in my presentation, because like that is actually an approximation of the entire thing, like using some polynomials. Just keep on reducing the degrees to make it simpler.
Is this should I share this one?
Yeah.
You can continue. If you want to use mine,
You're gonna use your laptop?
I think I'm gonna use this laptop.
Okay.
Everybody's gonna use it.
You don't.
No, I don't have
Use mine.
yeah.
I need
Possible.
to share.
We almost share one
Do we need to sanitize for that?
Wear gloves.
Wear gloves. Masks for your hands. Do you have the slides for?
I think I downloaded it.
Is it in the W5? Yeah.
Yeah, it's the latest PowerPoint, so it's
Okay.
W5.
Right. I'm gonna push those to the channel.
Oh, is this one?
Later, those of you in the Scribe team need to put all these slides in one place, or offer multiple ways.
By the way, the graph neural networks, has there been any evidence of it working well in the blind to graph models?
Graph models.
Like for example, node classification of any of those tasks. Is that like a state of the art?
I think it used to be, I mean, at the time it was state of the art. I think the paper, in also the paper they mentioned it with other methods like equal or the traditional node embedding. Yeah. So it was state of the art at the time.
I see. It's 2014.
It was 2016 when they also published the archive.
Okay.
Okay, hi everyone. I'll begin. So I'll focus mainly on the various algorithms to perform node classifications. By that I mean, so we can see that each node is like a single data point. Usually they have labels, and the ages represent relations between the data points. So in a way, like the difference between this and normal tabular data structure, for example, is that the fact that each sample is non-IID, meaning like information between related samples like might influence each other. So for example, if this is a graph of, I think, philosophical papers, and the age represents like citations between the papers, and I mean, if let's say the task at hand is to classify which subfield of philosophy your paper is talking about, for example, then it's likely that you'll be cited by other papers in similar fields, for example. So that way, like we graph data structure, we hope to exploit this kind of relations in performing whatever tasks we're required to perform with. Another example of this will be, this is like a protein to protein interaction graph. So like in human bodies, proteins tend to interact with each other. So when you want to find out about, let's say, what does this protein do, or what's the expression level of this protein, it tends to be influenced by other members on these nodes. And of course, we want to use the information that we have to improve like our predictive performance, for example. So I'll just go through this quickly because this has been mentioned before. But ultimately, our graph is a set and there's no natural ordering on it. And we want to define like new operation that is ideally permutation invariant, meaning like you don't want your operations to be influenced by the way you order your graph, for example. And it's also desirable probably to have like certain properties that normal convolution have, these things that Hoang has talked before, like shape invariance, locality, compositionality. So based on that, there are generally two ways of defining operations on graph. The first is spectral, like spectral method, and the other is spatial method. So I believe spectral domain we've discussed quite a bit in the previous presentation, but so maybe just okay, I'll skip this for this. So in spectral domain, we the way that people typically do things is to compute the graph Laplacian, do some eigenvalue decomposition to obtain like the Fourier basis U, then perform convolution on the Fourier domain. And as the first presenter has raised before, the problem with this is mainly computational because it's generally expensive to perform the eigen decomposition and also the matrix multiplication because we don't have Fourier transform defined in this graph setting. So then additional work that has been another work that people have done in that area is instead to approximate this expression over here that is computationally expensive with some other means of approximation that generally requires less time. For example, we can express the convolution here as a summation over here of a filter parameter theta prime with what we know as Chebyshev polynomials. So this is just a function that depends on the normalized Laplacian. In general, we can
set or bk over here to determine how accurate we want the approximation to be, and accordingly this will cut off the time complexity required to perform the convolution. And the latest work on this, I believe, is this paper by Thomas Kipp and Max Whelan called GCN, Graph Convolutional Network, which basically from this equation, you set bk equals to 1, and you do some renormalization trick, then you can approximate the convolution as the product here, and making this brief, we can have like our familiar feed-forward neural networks from this expression over here. But then again, this doesn't come without its limitation. And mostly the limitation is the fact that it's very hard. This method is inherently transductive. And what I mean by that is that, so when you want to compute the convolution, you need to find the graph Laplacian. And generally, so suppose this is our training graph. It has a unique graph Laplacian. You learn the parameter for this specific graph Laplacian, and you have another training graph that is different from, and you have a testing graph that has different structure from this one. You simply can't transfer whatever you learn on the training set here to perform like the inference. So typically what you can do is, if let's say in your graph you have some nodes that do not have information, for example, while other nodes have information that you want, you generally can extend with this method to make classification on the nodes within the same graph that you lack the information of. But generally you can't generalize this to a different graph. To generalize to different graph will be called inductive inference. And so this is what another method that I'm going to talk about, which is spatial-based method, typically tries to perform. So spatial-based method will operate directly on the graph structure. And so it is inductive in nature because you train on one graph, you can predict on other unseen graphs with different structures. And it can also be generalized to perform transductive inference. So the first method I'm going to talk about is called graph SAGE. The SAGE setting stands for sampling and aggregate. But generally what you want to do is for each node in here in red, because the graph data structure represents a dependency between the nodes, right? So there must be some way to aggregate the information from the neighboring nodes to make a representation about one node. Let's say we want to make a we want to find the representation of the node in red over here. My cursor is not working. Okay. We want to find out something about the node in red over here. So what this graph SAGE method does is you can either use all neighbors or you can sample like some neighbors, and you do some aggregation, meaning all the features from the neighbors of these red nodes over here, sort of aggregate them together. Then you can pass them through a linear layer, for example, to find out the representation. In this way, this aggregator function will sort of help to capture the information from the neighbors of the nodes that we want to make prediction on, thereby like exploiting the natural dependency that exists in this graph infrastructure. So this is the algorithm. So typically, let's say you have a network of sites, you have k layers in your network. So for each of the vertex, what you can do is first you compute the representation of the neighbors surrounding this vertex V. You aggregate all the information. This aggregate can be something like you take average of the representation of the neighbors of V. Then you concat like this, the representation of V in the previous layer with the representation of its neighbors. Then you pass it through nonlinearity and some linear layer, for example. Then after k step, you have like your final representation. So some choice of aggregate functions that you can use. So I've mentioned this previously. You can either, in order to find like the representation for node V on the layer k, you can either do an average of node V in the previous layer with all of its neighbors in the previous layer. You average them, pass it through some linear layer. The paper also did something like LSTM with a random permutation. So this is a bit weird because in LSTM the order matters, but in graph you don't have that ordering, but they do it with random permutation. Another one is you can do some kind of pooling. So for node V on the layer K, you can find the maximum of its neighbors, and you can concat it with node V on the previous layer. Then you pass it through a linear layer, for example.
So each representation of the node depends on its neighbors' representations, right?
Yes.
But how do we initialize the representation? Like, yeah, like one of the nodes representation in one of the nodes representation we find through some weights and other nodes representation, right?
Oh, so probably it's just the feature vector, I think. It's just the
Oh,
feature vector. So
then we learn it.
yes. So like when K is 1, this H0B is just like the feature value.
Oh, okay.
Then you keep propagating that across the years. So this framework can also be used to do representation learning. Basically, the difference is just the objective.
What's the LSTM? LSTM on a random permutation.
So you apply like just normal LSTM, but because LSTM you require some kind of ordering. Like in this paper, what they do is they pass it sequentially, but they permute, like they randomize like the way they pass the information to the LSTM.
But LSTM, like you have the target, like the target node V there.
Yeah.
And then what comes up? Then you calculate some function there.
So they're saying, okay, you take the node V, and then you take all of its neighbors, but you just put it in a set.
Yeah.
Draw them one by one.
One by one.
And
Then you build the
keep it.
LSTM. Okay.
Right. So if the node V has 10 neighbors, then you
Yeah.
start with V, and then you have whichever with the cable is all the way to the last one. That's what I mean.
That's what I understand.
Also, they could do the attention thing, no?
Oh yeah, that's the paper after
The
this.
paper.
Put attention.
Yeah,
They did attention as well.
So you're jumping the gun, which is always a good thing.
Yeah, but I guess like the main takeaway of all these graph methods that we will try to learn is to define an operation that somehow aggregates information from all the neighbors. So one way is you can define like an aggregation function that a simple one like mean or max, or to extend this you can parameterize them like in the case of attention. So that's what generally people have been doing. But this can also be used for representation learning. You just have to change the objective function. So typically the kind of objective that people do is this one over here. So if we break down the term, this is actually equivalent to maximizing the likelihood of, say we want to find a representation of node U. So we want to make sure that the representation of U is similar to its neighbor V, this example, and at the same time it's far away from nodes that are not its immediate neighbors. Yep. Okay. So this is the next paper, which is called GAT, or Graph Attention Network. So the difference between this and the previous one is only on the way they aggregate the information from its neighbors. In this paper, just like in the attention paper, what it does is for node V, you compute a weighted average of all the neighbors of V, including itself. And this weight can be learned through this expression over here, which basically you sort of and this weight over here is something like you try to find the similarity between V and its neighbors, and you pass it through this linear layer over here with parameters that you can learn. Then you just compute this expression over here. Then the output for that node V will be just Oh, and in the paper they even implement like multi-head attention. Basically, you just have k different attention heads. And you concatenate the resulting result to pass on to the next layer. Yep. Okay. So that's all for defining the answer. Any
I
questions?
didn't understand the previous slide. What is the presentation learning?
Oh, okay, this one?
Yeah.
Okay, so you want to minimize this objective. So, which is,
Where is coming from? Why did you choose this?
so what I want to say is that you can just use this aggregation function for different kind of tasks. And you can even do it for representation learning. You just have to change the loss function basically. And this is I'm just giving the typical loss function that people use to do unsupervised representation learning, which basically is just saying you want to maximize the likelihood that a node U, they should be similar with its neighbor V, but it should be far away from nodes that are not its neighbors. Basically, I mean, if I'm to summarize this equation, it's something like that.
But maybe I don't know this term representation learning. Like more broadly, what does it mean? Like in the
The thing with this is it's something like node embedding,
Yeah.
right? You want
them to
to
represent like each node.
because your
Uh,
data is a graph, right?
Yeah.
It would be nice if you have like some.
I was like in autoencoder. No, I don't.
And actually, yeah, autoencoders they're trying to compress the nodes into like a smaller representation, which is also a form of representation. Like a bottleneck layer is the same thing.
You'll talk about that as well later.
Yeah, we'll
Yeah.
get that.
Okay, so any question? Any more question on this JV model?
So how many attention heads do they recommend? I mean, it should be very specific to application. Do you remember anything about what they said?
Let me check. Remember.
Okay, no
It's-
worries if you
yeah.
don't remember. I mean, our support staff can go figure that out. Yeah. So I mean, last week we talked about multi-head attention transform and what it's doing, right? It allows you to pay attention, but not make a commitment on what is important as a downstream layer might consider something that's important. So I think that's the same logic here, right? Like you're looking at different neighbors of the node in the graph. But for a particular application, certain neighbors may be more important than others, right? So you're not making a commitment using something like multi-head attention. You say each head can pay attention to whatever it wants, right? Which is good for its downstream layer. Right?
Can't remember if they allow you to stack multiple layers of JT. Like for GCN and graph stage, you can stack multiple layers.
Oh,
right?
yeah,
If
you
they K equals 2, then your representation is sensitive to neighbors, second order neighbors. But for this one, is it possible?
I think it's possible.
Okay.
Yeah. Because I mean you just have to do it to do this sequentially, right? Like
Oh.
let's say for the next layer, then this HU here will be the output of the So for this first layer, this HU will be just a feature vector, and for the next layer, it will be just the output of whatever the previous layer attention gives you, I guess. If I'm not mistaken, they use like 2 to 3 layers of attention. I don't remember exactly.
So then eventually you just want to classify each node.
You just want to classify each node.
So it's like you're running like treating basically each node as like as an observation, and then put the stuff around it together, and then run a completion authority.
Yes.
Is this inductive?
This is an inductive case. Because like if you notice, this doesn't depend on the size of the graph. As long as you know the feature vector of this node and its surrounding neighbors, you just need to pass it through the network and it will give you some representations.
But then in a sense, it's a little bit like natural language processing. It's like you have a sentence and then you have a bunch of like words, and then like you know how words are connected. And then, I gave you a word. I want to know what's the likely neighbor
It's like distributed representations of nodes, right? It's word to byte or something.
Yeah.
I think they use similar techniques, right? Like negative sampling, and yeah,
Yeah.
it can be treated as similar.
It looks very similar.
But I'm also curious, what's the, let's say for natural language processing, what's the advantage of this over representing the data in the usual way?
What's the usual way?
Oh, I mean like when you have like sentence in vectors, as opposed to, is there any benefit that if you represent sentences as words on graph?
Oh.
I don't know.
But it's like maybe like you have a bunch of networks. Like you have your Facebook Facebook friend network, and I have a Instagram network. I have a Twitter network. Then let's say I want to predict, like let's say you are in all of these networks, and then I want to predict, say, if you're friends of somebody else in a different network I haven't seen. Then you could use like some like
I guess this kind of approach.
Inductive approach. I think for your question, there's a paper I sent.
Yeah, so actually the paper, the next one I'm talking about sort of deals with that, but yeah, so I'm kind of jumping ahead. So I'm gonna talk a bit as well about one application paper that tries to use a graph convolutional network to perform what we call emotion recognition in conversation. So the problem setting is you have M speakers and you have N utterances. So these utterances, I think, is just like a series of words before you pause. So each speaker, the context is each speaker speaks, they utter certain sentences to each other like in a temporal manner, but each utterance has a label which corresponds to the emotion. So it can either be, so when you say like my head is aching, your emotion is frustrated. So they want to classify this in a conversation between M people. So the way they model it is, first, what this paper does is you use a bidirectional bidirectional GRU to learn the representation of each utterance. So this is just for input to the graph later on. So each utterance UI, you encode this for GRU with a context size of 1. So take into consideration like its immediate +1 and -1 utterance, and you learn the representation for each utterance. Then what?
So an utterance is an entire phrase, right?
I think it's a phrase, yeah.
Okay.
After you learn the representation, then they sort of form a graph out of that. So let me try to explain this. So this is some definition in this. So this is some notations they encountered as I go through the paper. So basically, if you look at the picture over here, this G is the representation of each utterance as outputted by the previous GRU network. The color here represents the speakers. So this graph is formed. So this is a directed graph, meaning when a phrase is said before the other phrase, so there will be like a direct H between the two that describes the ordering, and there will also be directed H, and the graph is colored by like who says which word and things like that. So what the paper does to classify this is, so the idea is like, because first the speaker matters, like who speaks the word matters. It influences like how you perceive. It influences like the emotion that is contained in your phrase, and then it's also like the neighboring phrases that you say also supposedly influence the emotion that you feel like for a certain phrase. That's why they model it in this graphical manner. So the way they construct the age is also based on the context window of size 10. So meaning like phrases that are said like meaning you don't form like an age between two phrases that are like 10 phrases away or something like that. So I think it's just helpful. So then the way they learn, so the way they do the aggregation here is similar to the way they do the attention before. So let's say for each phrase I, then you have a representation GI for it. You pass it, you do something like an attention mechanism. You do a weighted average on each on the surrounding sentences. That is also dependent on who say the words or what are the words previously. Yeah, then you just like you just stack this operation further for like classification in the end. Yep.
So one question. How does this model maybe as compared to bird? Did the author mention that?
So the author did compare this with, they didn't compare with bird, but the model that they compared with this is something that is just purely based on attention model.
Like a sequence to sequence RST.
Yes, yeah. So the author showed that this outperforms quite a bit, I think.
How do you plan to apply bird to this? Like to represent each utterance or represent?
Oh, sorry, no, like by feeding the data through bird and as compared to the way they're representing using this application. Because it's emotion recognition. There's no reason why we can't use bird as well.
Yeah.
Again, feed the whole dialogue into bird.
Yeah. Maybe the questions answer and then into bird.
It doesn't. I guess if you feed it like sequentially, it doesn't capture. But in fact, you can only have the sequential tables, right? But I mean, some of the graph they model the dependency quite often. Yeah, maybe. Yeah.
Yeah, that's true. That's one constraint. Can't be having like a one bird every single time step. That'd be so expensive.
But I mean, for each utterance, is also they also have the author information, right? Which author. But for bird, I mean, I think you can generalize it into any sequence to sequence learning. But I think for probably the pre-trained model only works well on language model. How can you? I try to encode the whole language under the whole conversation.
The conversation is still half problem. They can't be addressed by bird.
Of each utterance is very important. Include the vocabulary.
Does it work?
Yeah, I did the experiments of their machine reading comprehension. I use bird as a reporter as a decoder and the whole dialogue.
So you say you use birds for machine reading comprehension.
Yeah, whole dialogue.
And you use the output of the encoders and do a classification. Is that what you said?
The independent is a whole dialogue. It's utterance.
I see. So every single utterance you concatenate output of the word, concatenate, and then you do classification. Is it?
No, that is just the span from the
So you inputted with the question, right?
question and
Yeah.
you output the span of answer in the dialogue.
So in then you just get two outputs, the start and end indexes, right?
Yeah. And the analysis is that the speaker of each utterance is very important. Simply concatenate each utterance is not very useful because we don't adopt the speaker information.
So
And the dialogue JSON also highlight the speaker of others.
Yeah. But can't you do the same and then using like sequence model? You just like add some speaker level embedding as a feature. Would that help? Yeah, that works with it before.
I guess you can do some kind of self-attention and transformer.
Yeah.
But I mean, the idea of Bird is pre-trained language models. Right? You have to apply it. Like,
you could also apply self-attention and multi-heads to LSTMs, but that would be just again.
Yeah, okay, that's all I have.
Okay. 5-10 minutes real quick.
Are those slides on Office also on Slack?
Yeah, we've downloaded it. Yeah, correct. Okay, so I'll be talking about a little about the graph embeddings. The idea behind a lot of different graph embedding methods is actually based off word to vec. Maybe just a quick refresher on word to vec. It's, for example, you can have a window of words, and in those windows itself, you take the surrounding words to predict maybe the word in the middle, or you could use the word in the middle and predict the surrounding words, and you train it with a large corpus, and that's how you get like a word to vec kind of embeddings for words. And then recently, people have decided to apply similar architecture to graph models as well. And one of those is called deep walk. Think, for example, if you have, okay, maybe for example, for word to vec, if you have like maybe M customers, and for every customer itself, you have a history of XI transactions. So you could using those transactions as a sentence, you could learn the representations in the same way. Similarly, for DWalk, the idea of DWalk is that you have a graph, and maybe, for example, if you represent each node as a word, the idea of DWalk is to have a stochastic process within it itself, and you can maybe start from a random node, and at each time instance, you have a random element to say which direction you want to go to. And this is how you can generate a sentence. And the sentence length of the sentence is also like a hyperparameter in which you can tune. And after you have this kind of sentences, you can train it the way you train a word to vec, and that's how you can have like a word to vec kind of representation, but generated with a bit of a randomized element in it, which is the deep walk. Then people have started applying one of these methods to graph, like for example, the input karate data set is just like a karate data set, and they represent all of the nodes in a 2D representation. And indeed, you could see that they could capture some sort of cluster and spectral dependencies within a 2D representation, which could be quite useful if you want to do some sort of node classification or as like a feature represented for any of your tasks that you want to do.
Sorry, what is this karate graph?
Oh, I'm not sure about the details of the data set itself. I just taken off the.
You can think of this as the MNIST of graph
Yeah.
data. So it's like a small data set where you can technically look through each example and play with it. So this one is about Jackery's karate club, like the member of the karate club, and then how they are connected to each other. And you can see, I think there's two natural community formed by the two admins of the karate club.
I think it
You
was
can
something
see it on
to-
Slack. So Shenting just put. Yeah.
Oh,
I think they are like within a karate club who were together.
yeah.
It's a it's a famous.
It's the evidence of I took it from the paper, so but exact columns represented in the data set not sure. You know like what are the relations and all that.
I think that, I can't remember, but they have some relationship.
Yeah, that kind of stuff. Then Deep Walk I think was 2014, and Word to Vec was like about 2013. And then after that they have a Note to Vec, and the difference between Note to Vec and Deep Walk is actually pretty similar. You have in a way think about it as you have exploration and you have a return rate. So at every single time you do a random walk, you base off these two parameters. So if the probability of return is higher, you go back to the same node itself. Otherwise, you explore further. So it's like you set the two different parameters for breadth search and depth search. And by tuning different parameters, you can see that you can capture different representations. And for example, if you have like a higher exploration rates, you could have clusters that forms and spans across further regions of the graph itself. Similarly, if it's you have higher return rate, it's more like all of your clusters it's centered within like a region. So yeah, just different parameters just to tune the parameters. It's not important. Oh, you could also apply this to like a weighted graph. So just now I mentioned that you have like a exploration rates and you have return rate. So if you have a weighted graph, you just multiply the weights to the rates itself, and that's going to determine how likely you are to go to different nodes. And it works quite well. I'm not sure what does.
Like this is very similar to PageRank. Little bit, no?
PageRank, yeah, actually, the idea is the same, where you have you keep iterating and yeah, it's very similar to PageRank. I forgot the mathematics of PageRank. Did PageRank have a random walk?
Yes.
Yeah.
Yes, right. Yes, right.
Yes.
Yeah. So
And then I think they take they transform the matrix somehow, get the value.
I think they
key
find the
thing about-
eigenvalue.
Yeah, the key thing
Yeah.
about PageRank is you need to add to make it ergodic. So that means every node has to be reachable by every other node. So
Yeah,
they
but-
do some smoothing, right? So they say you have the original probabilities, but you take a small minute part out of those original probabilities and you spread it uniformly out. So you allow every node to be connected to every other node. That allows a stationary distribution to result from the random walk. Otherwise, it may not converge, right? Like you have a sync node that has no outgoing edges, then all the mass will aggregate there. So that's the reason why they do PageRank in that translation. There are lots of other variants of PageRank that go on the site.
So like then it's like doing PageRank, then you get the Markov matrix, and then you generate sentences at random.
not exactly a Markov chain kind of stuff. It's more like you generate like a sentence, and the sentence you train it the way you train a word to back. I think in PageRank I remember vaguely that there's a teleport element or something.
Yeah, but I mean like I just think about different way of running the same algorithm. Maybe if you start with the matrix that represents the PageRank. I think the main difference is like it's a Markov chain, and then it has a teleport mechanism. But like it just represents probabilities of traveling anywhere in the graph in a stationary mode. So I guess like you could also maybe construct this matrix and then generate sentences as many as you want from this.
Yeah, that's the idea. Yeah.
And then do the embedding. No, I just thought like it was interesting. I was like, and then probably doesn't have. Probably it's not very.
I'm not sure if the
necessary.
author has has thought about this PageRank thing when they are trying to construct the book. Maybe I go back and take a look into it. There's also text rank. It's also quite similar to PageRank. It's just for text. So yeah, maybe it's a good thing that I'll go back and think about this thing. But if you return to this discussion, Note to Vec, it works better than Deep Walk. I'm not sure what data set is this, but it's like a multi-level classification problem. So what they do is that they try to embed each node and they do a classification on it, and the result is it's improved. So you can sort of
They use like what classifiers?
that I'm also not sure. I couldn't really find what classifiers they are using, but maybe I don't think it matters a lot. Maybe you could just think of it as a logistic regression or something.
So I want to mention another rank. It's kind of like PageRank. Another is called LexRank.
LexRank?
Yeah, it's more kind of like two-back. Probably you can check. LexRank is to find the similarity of between each of two nodes. It's kind of like the two-back. Two-back is based on the graph network.
LexRank to find node similarity.
Yeah, because in TextRank, is to generate a window to calculate
The relationship between words.
Yeah. But the next one is another way, just to compare the future. You can call it the future of the two nodes to calculate their similarity and generate another graph structure. I think it's probably more similar to what you said now.
If you talk about similarity, it's indeed quite similar. If you have an embedding for every single node,
Yeah,
it's just one more step to come.
Yeah, in this way, you do see that in other, just use a score or something.
LexRank.
So you can look at LexRank, you can look at PageRank. PageRank predates LexRank, and then TextRank comes after LexRank. So they're ordered chronologically. People who came up with PageRank are, of course, very famous. Sergey Brin and Larry Page, right? To make the foundational Google algorithm from their previous work on backup, which was their Stanford indexing system. Right? And that itself actually comes from the roots from bibliometrics, right? The people who came up with this idea of ranking things that were actually scholars who were studying other scholars and finding out why people are more famous than others. Right? So the whole point is like, if you count citations like the scholar does, it's misleading. Right? Like I have a lot of citations, but I'm not very famous, right? So it really depends on like who points to you, like whether those people who are citing your work is famous or not, right? So if like say you write 10 publications and you cite yourself many times, you get a lot of citations, but nobody cares about your work, right? That's no one's citing it besides you, right? So the important part is it's a recursive definition, right? You are important because important people cite you. And how do you determine whether somebody else is important while using the same definition, right? So there's a lot of this type of circularity in these types of random walk algorithms. And so you can generalize that to things like PageRank and LexRank, where you're saying, let's not think of node in the graph as a person, it could be something like a sentence, right? And these methods predate the change of NLP architecture into deep learning, where now we use embeddings, right? Embeddings are sort of a contextual representation. And that evolution of embeddings came from the idea of representing context using random walks, okay? So random walks are a precursor to what we know about embedding technology. So it's interesting to see how things evolve. Because now we're studying deep learning and say, oh, well, we want to go back to random walks. And actually, that's ancient history by CS techniques. Right? Okay. So it's interesting to know the evolution and why one thing evolved from each other, because we keep on rediscovering the same types of issues. Yeah. So random walks themselves are very interesting. There's a lot of different ways you can do random walks. So PageRank is sort of like the most basic vanilla algorithm, but there are lots of variants. For example, there's focus PageRank, which says that certain nodes in the graph are more important than others. So let me just briefly tell you about that. So in PageRank, you add a small smoothing transition probability to all nodes, right? So you get the entire graph connected, So it's a K-complete graph, but with very small edge weights for things that weren't originally in the graph. So you're hallucinating new mass, right? And then what you're trying to do in focus page rank is say that we don't want to add this uniform probability to all nodes. We want to rather think about adding uneven distribution to all nodes. Okay, so the random walk model came out of this idea that you are a web surfer and you're following links on web pages to other pages, and that's why you follow a random walk, right? But once in a while you start over. And how do you start over? Well, you start over by picking a random page on the internet, on the web, and starting from there, right? That's the analogous idea. But if you think about it, nobody really does that, right? So like say if you're an art major, you might start from some art history website. Or if you're a CS major, you would start from archive, right? So certain websites on the web are more important for certain subject matter. So the idea of focus page rank is say, depending on a query or depending on the topic, you would start from a certain set of pages more than others, okay? So for example, if you have a query that's, we can say is a CS related, then when I do the random walk, I allow you to restart only on pages that are related to CS with a higher probability, and ones that are about arts or finance or I don't know, Singapore, coronavirus, a much lower probability, okay? So there are lots of different mechanisms for random walks. It's a very interesting field.
Yeah, and if you guys are interested to check out what's after Node2Vec and Deep Walk, that's SDNE. I'm not sure what SDNE is. Struct2Vec, it's more like structural identities, where if you have a graph with different identities and maybe lockers or policemen, even if they are far apart in the graphs, they want to find a way to represent them in a space that's close to each other. That's the idea behind Struct2Vec. And I'm just really curious about these graph embeddings because it's my first time seeing them as well. So I tried to implement them and see the result for myself. And I'm working with some news data right now. These are all the stock market articles, the company's articles, and indeed using Node2Vec, I get very similar representations with when I train my own embeddings with with the idea of Doc2Vec. And but the difference is that Node2Vec I could train it in less than 1 second with my laptop, but embeddings with like a Doc2Vec ID kind of methods took like a whole day. So it's interesting. I've not tried applying this kind of stuff to classification or my own tasks, but it's quite promising. And Struct2Vec is interesting that give me clusters, and those clusters actually have meanings as well. I've just sort of quickly glanced through it, and maybe like for example Tesla, it's more closely related to tech kind of stocks, and the meaning is sort of embedded within the clusters, and like Amazon, Apple, Google, they are sort of in the same cluster. So I quite happy to see this. So
what are the clusters here? So what's like the right cluster?
I'm not sure what's the right cluster within like the companies. Could be like the categories that each of the companies are in. Intuitively, I would expect like Apple, Tesla, Amazon, this kind of high-tech stocks that has high volume in the news would be the same cluster. And indeed, Apple, Amazon, Google, Facebook, they are all within the closest range. Sorry, it's very small. But if you guys are interested, could even send a code to you if you want to. But oh, I'm sorry, I did not explain the data set. It's I took my news data set and sort of built like a co-occurrence matrix of all of the companies, and using this co-occurrence frequency as the weight of the graph, and I just project it with Node2Vec and Struct2Vec, and this is the result. So it's quite interesting.
So each node is a company, and the vertexes are how many times
They
they are.
co-occur with each other in the news. Yeah. So it's quite interesting, and this is the a picture of all the companies in Nasdaq 100. I'm gonna try it with the S&P 500 and see how it goes. I'm also working closely with news data, so good.
What was the method you were using before? You said you took a day for doing what?
Yeah, I'm not sure if you are familiar with doc to back. Have you heard of that word before? So doc to back and the word to back is very similar, except that in doc to back you try to have the ID that represents each document itself. So whenever, for example, you have a sentence in this document, you find a way to say, hey, this is from this document, and you train it together with the method of word to back. So in the end, what you get is that you also get the same embeddings as you get from word to back, but at the same time, you have an embedding layer that represents each document. So, and that's the idea behind it. And that thing took like a whole day. This thing took like a second. Just press enter. The thing outputs the results.
So then, sorry. Okay. So in the doc2vec, you also have the representation of the individual words, and that's how you kind of put them in the 2D, right?
You trade it like maybe in 10D or 100D, and then you just TSND.
Yeah, I mean, okay. I see.
So why is it so much faster?
So when I'm training embeddings, I'm also training together with the text data. But in this itself, I'm only training with the co-occurrence graph. So immediately the results is actually very similar. I'm also quite surprised by how similar it is. And
but I didn't understand like the doc to back to trying to assign embedding for a document. But here you like looking at company names.
So think of each news as a document, and that document represents what this news is talking about for which company.
So each document you assign to a company's name, or like
correct.
company.
Yes, and assignment is not done by me; it's done by the news agencies itself. Like for example, Reuters. I scrape that data, and they have already labeled all of these to be like Apple or Amazon. So it's intuitively when I read through the news, it's quite it makes sense why they assign these news to certain companies, and the person that's assigning it's the person writing the news itself. So
okay, so then the note you make, you extract the company name from the text or from the document?
Not the company names.
Okay.
It's like for example, this news it's about Amazon and Apple.
Yeah.
So I will be using these two companies as like a one frequency, one time of co-occurrence. Not to say like the names that close to each other.
Yeah.
That they will be quite dense and may not be accurate. You gotta do some pruning if you do it that way.
Okay, but then since that you were doing quite different things.
Quite different things.
Because like when you're trying to determine like co-occurrences, if you can embed the code, if you can maybe like embed the company name, but then the document you're trying to embed the document. So I didn't
Document is trying to.
I didn't understand what the analogy between.
I agree with you that they may not be very similar tasks, but in doc to back, I also want to train the word embeddings, right? So it's like I might as well also get something out of the documents, and surprisingly, I just want to see like compare with these results, and surprisingly, it's very similar. So that's why that to me is also a surprise. But maybe a co-occurrence frequency like this can also capture relationship dependencies, which is a very simple weighted frequency between the companies.
If you're only interested in the relationship between the companies, slowly taking the embeddings will be enough. Right? I mean, this embedding space is only valid when you want to compare between companies, not between companies and some words. You're not training words in your code. Right? Say, I want to compare something like Apple and technology. Right? Can I embed technology to this? It's no perfect. I cannot because there's no concurrent matrix on the word.
That is true. Yeah. But my thinking is that, for example, for doc to back, what the model wants to learn is really up to the model, and somehow they projected the same space, and indeed it looks just like that diagonally. And the positions is also some of the companies is also very similar. So I'm not sure what the model is trying to learn, but it's very similar to note to back in when I train it the same way. So that's the idea I'm gonna bring across. So you want it? I just send it to you.
Wait, which note to back implementation are you using? You're using the one Stanford?
There is one from GitHub. I forgot the name of that guy. I just took his quotes for granted. So if you want, I could check it and tell you. That's what I think. Yeah, that's all.
I don't know.
Professor left, right?
But he loves his computer.
Oh, I have to leave first. Please help fix after that. Okay. Then we're done.
So whose computer is this?
Oh, it's mine.
Oh.
I mean, it's his, but mine.
I just want to ask you for that. Oh yeah, sure. You want to say you said it's not a knowledge graph, but you also represent relations.